Okay, thanks everyone for coming. If you're watching the replay of this, which just by the numbers, it's likely that most of the people watching this are watching the replay of this. If you're interested in seeing these seminars happen live, you could join the Patreon at the 2 top tiers. And my goal for this semester is to do these maybe once a month, or maybe once or maybe twice a month at the most. And so just a heads up, if to look for these in the future, these Patreon seminars. Okay, so today's talk is given by one of my former students from Colorado College, who is now at the Colorado State University, Nate Mankiewicz, who's been doing some interesting stuff related to the geometry of big data, is what he's told me. And so maybe we'll let him start.
Cool. Yeah. Thanks, Michael, for the introduction. Yeah, so today I'm going to be talking about subspace and network averaging for computer vision and bioinformatics. So really, we're just going to be talking about fun ways to calculate averages or central prototypes. This is work that obviously I've done, and my collaborators are also listed here under authors, Doctors Emily King, Chris Peterson, Amy Peterson, Eric Kehoe, and Michael Kirby. They're all from Colorado State University, and now I think Amy Peterson works at State Farm, and Eric Kehoe works for Zoetis, Kehoe works for Zoetis. So yeah, and feel free to stop me at any point and ask questions. I know I have way too many slides, so yeah, I'd rather have a good discussion rather than just motor through a bunch of stuff that is incomprehensible. Okay, so without further ado, this is the outline. So I'll give you guys a short introduction to this sort of stuff, these sort of calculating averages. And then we're going to talk about subspace prototypes, which are sort of averages of collections of subspaces. Then we're going to talk about this flag IRLS algorithm, which is an algorithm to calculate certain subspace prototypes. Then we'll talk about this thing, pathway expression analysis, which is sort of calculating prototypes of gene expression data. Did I just drop sharing? Let me see. I'm sorry about that if I did. No, I'm still sharing. Good. Yeah, so prototypes of collections of genes, that's pathway expression analysis, and then module analysis, which is also sort of prototypes of collections of genes. And then we'll go into a conclusion. Okay, so to introduce, just to overview one more time, we're talking about 4 new, in quotes, central prototypes or averages. The flag, median, and maximally correlated flag are going to be averages of subspaces, whatever that means. Then we're going to talk about the cluster expression vector and the eigengene subspace, which the cluster expression vector is going to leverage graph theory. The eigengene subspace is more about, is another subspace prototype. The mathematics we're going to be working with is optimization problems. We work with optimization because this is a good way to like mathematically formalize these central prototypes. We're also working with the iteratively reweighted least squares and clustering algorithms. And we'll also do a little bit of graph theory, at least mention it. The applications here, as I said before, we're going to be talking about applications in computer vision. So these are data sets of images and videos, and bioinformatics, which in this case is in general multi-omics data sets, and specifically what we call transcriptomics data, which is like, I guess, gene expression data. Okay. First off, this application, as I said before, we're going to be talking about computer vision data. Like, so I'm an applied mathematician, so I really care about applications here, right? So we talk about computer vision data here. This is a 2 different data sets. And essentially in this type of computer vision data, you have a collection of short video clips centered around a person performing an action in the video. And they're labeled by the action that's being performed in the video. And our goal is to cluster these data sets based on action, or provide some sort of clustering and see how good it is with respect to these action labels. And with bioinformatics data, specifically transcriptomics data, which is a subset of these multi-omics, these are just long words that transcriptomics, just think gene expression data. There's kind of two things we're working with. We're working with, we're going to do two different sort of tasks. The first one is pathway analysis, where you take a collection of genes that are known to cause some sort of biological process, and then you do some analysis with genes based on their memberships in these pathways. And also module analysis, which is like, rather than working with genes that are known to cause a certain biological process to happen, you work with just collections of genes that are related to each other based on some sort of data set. So sort of the pathway-based work is collecting genes into groups based on known biological structures, whereas module work is more data-driven. Okay. Finally, we get to start talking about a little bit of math, but the math maybe that we learned about quite a while ago, I would say, for probably most of us. So just kind of a review, like central prototypes or averages of a probability distribution over R. I'm going to use the word central prototype for the rest of this talk, or just prototype for these things. So in general, if you have a probability distribution over the real numbers, right, you can calculate different types of central prototypes or prototypes. You can calculate the mode, the median, and the mean. And depending upon the shape of the distribution, one of these is a better representative of the center of the distribution. So in this case, we have a bunch of outliers. So the mode really sits at the peak here of the distribution, whereas the median is slightly pulled toward the outliers and the mean is pulled a long ways to the outliers. So having like different prototypes, right, for a probability distribution or a set of data is important, right? Because depending upon how the data is structured, one prototype could be preferable over the other in terms of like a representative for your data. So let's up n dimensions here. So rather than working in the real numbers, let's work in the n-dimensional real numbers and take a set of points, p of them, that all live in the real numbers. We're going to call this set of points A. And now we're going to do central prototypes of this set of points. So no longer continuous probability distribution, we're going with discrete, and its support is over Rn. Okay. So let's just list out a central prototype. And I said there was going to be optimization. Here's the beginning of optimization. And we're going to talk about the optimization problems associated with each of these central prototypes. Because the central prototype is a solution to an optimization problem, or it can be written as such. So the first one is the centroid. This is like the generalization of the mean. It's just a vector in Rn that minimizes this cost function here, which is just the sum of the squared distance between each one of the points and your prototype. So you want the centroid really is the solution to this problem. And if you write out what a 2 norm squared is, and you take the derivative and set it equal to 0, then you would exactly find the centroid, which is literally just adding up each one of these data points. Y would just be the centroid, which is just adding up all these data points and dividing by p. So quite easy to compute. There's a unique solution to this problem. It's nice in many ways, and it's commonly referred to as like the average of a set of points, right? So that's a generalization of the mean. We're not going to talk about the mode here, but let's at least talk about the median. If you generalize the median to Rn, it's the same optimization problem, but you just drop the square. And you'd think like, oh, this is such a small difference, but in fact, this has consequences to the objective function landscape. And in fact, for certain configuration of points, you might lose uniqueness of the median in Rn. So there might be multiple medians, which is kind of weird. And you also have this restriction, right, which you didn't have in the centroid, where the median actually has to live in your set of points A. So the median isn't quite as nice, but we know that in probability distributions over R, right, the median is less affected by outliers, so it could perhaps be like a more robust notion of center of a set or a cluster of points in Rn. So, okay, there's the median. What if we remove this restriction that y needs to be an A and just optimize the same objective function, which is this thing here, or cost function, over all the real numbers? Then we get this thing called the geometric median. And I guess now it's just the median, but it's optimized over all the real numbers. Again, the median and the geometric median are not convex, and hopefully we'll get to the point in this talk where I get to talk about algorithms for finding the geometric median, because in fact, just taking the derivative of this objective function and setting it equal to 0 and solving, you can't just solve it. You can develop an iterative scheme to give you an algorithm to find the solution to this problem. There are also ties, if you guys are interested, between like the geometric median and I think these things called Fermat-Weber points and other topics in mathematics that are interesting. Okay, so what I've been working on is not the mean, the median, and the geometric median. However, I've been working on 4 new prototypes in Rn, which I just briefly mentioned at the beginning of this talk. So we have to do some setup, and then we can formulate these prototypes in Rn. And then throughout the talk, we'll talk about perhaps the subspace prototypes and how they work in that setting, and also this sort of graph theory-based prototype as well. So we're taking a set of points in Rn, and we're making a matrix out of them. We've got P of these points. And if we mean center the rows of the matrix, we're just calling it X hat. Okay, now we're gonna just make each one of these vectors unit vectors and call each of these unit vectors U. So that's what we're doing. We're just dividing by the norm. Okay, and then this is a bit hectic, but essentially I'm gonna take these scalars Ci, which are gonna be associated with each one of the points. And they're really the centrality of each of these P points in a network of these points. So we can talk about how to generate a network from data. We can talk about notions of centrality. And I think today we probably don't have time, but if you have any questions, I can discuss it further. But essentially just think about these as just weights that have some sort of, that are based on the structure of your data. Okay, so we'll introduce the name of the new prototype, the optimization problem that it comes from, and the application. Okay, so the first one is the flag median. And again, we're thinking about this as a prototype in Rn. We have this like unit vector constraint in our optimization problem. So in this sense, we're trying to minimize this function here, but over all points y and Rn that are unit vectors, or y transpose y equals 1. This is the same as being a unit vector. And yeah, this is the optimization problem. And there's ties between this optimization problem and the angles between these unit vectors. And this is kind of where subspaces come in, and we'll talk about that later. The application of this is in computer vision. Okay, so now we have this thing called a maximally correlated flag, which looks really similar, right, to this original optimization problem. All I did was remove the 1 minus and switched it to a max. And you'd think, well, like this is almost, these should be almost the same problem. You just, you can minimize 1 minus the thing, or you can maximize the thing itself, right? But since we've got this 1 and this square root, these actually turn out to be different central prototypes. And in fact, the flag median is much like better behaved than the maximally correlated flag. Cool. Another application in computer vision. Now we have the cluster expression vector, or the path. I'm going to also call it the pathway expression vector, depending upon what we're working with. This is a bioinformatics application, and this leverages these weights, which come from centralities. So this is really the exact same as the just calculating the mean of the data, except we're weighting each point based on its centrality in a network of p nodes. And the centrality, that carries the biological information of each of these points in terms of how they're related to one another. So it's almost just a mean, almost just a centroid in Rn, but it's a weighted centroid and the weights are special. And then finally, we have this thing that's called the eigengene. And this is something that people have been working with since like 2006 or 7. But it turns out that the eigengene doesn't necessarily have to be an Rn, and so I call it an eigengene subspace. This is another like subspace prototype, like the flag median and maximally correlated flags. Again, we're going to formalize subspace soon. And the eigengene subspace is the solution to this minimization problem. I believe this is actually, there's my first mistake. There's always mistakes. This is actually a maximization problem here. So my apologies. This should be a maximization problem for the eigengene subspace. Okay, moving on. I'm going to start talking about subspace prototypes. What questions do you guys have so far?
I was wondering, like, oh, there I am. Do you have some sort of like intuition for what this would look like in, say, R2? So do you have, I don't know if you have anything like this prepared, but like, what does it look like if you put just a mess of points in R2 and then calculate these polytopes? I mean, each of those polytopes would be points in R2, right?
Yeah. So
like,
yeah, you mean what are these prototypes you mean? Yeah, like what would happen if you, yeah, I mean, sure. Yeah, there would be points in R2.
yeah.
And yeah, I mean, I think there's a lot of like geometric intuition that you can get from each of these.
So like
in R2,
if you took like a bunch of points that made a circle, obviously we're taking finitely many points, right? But just take a bunch of them, so it's like approximating a circle, right? Then one of these would probably be the center, right?
Yeah.
Or maybe all of these would be the center because that's such like a well-behaved data set. But you know what I'm getting at?
Yeah, well, in fact, not quite, right? So if you sample like noisy points along the unit circle, for example, right? Each of these are subspace prototypes in R2, right? So in that sense, we have this constraint on the prototypes that they actually have to live on the unit circle.
Oh,
because they have this one norm they have this 2 norm constraint. And so if you took a set of points, let's say just on the upper half circle, right?
Yeah.
And you're calculating, like, let's say at least the flag median, maximally correlated flag, or this eigengene subspace, again, this should say max. Then that would live on the circle probably about in the middle of that arc.
Okay.
Whereas the cluster expression vector doesn't have this constraint. And I would expect it to be more toward like the origin. And so there are good things and bad things about this, right? These constraints assume like having these, what in general are called orthogonality constraints. They assume that your data like lives, that a data point, the data point 1, 2 is the same as the data point 5, 10. In the sense that like AB is the same as X times A, X times B.
So R2. You're averaging directions almost instead of points.
Exactly. And how do you average directions? You use angles. Yeah.
Okay.
So, and that's what we're going to talk about now is directions.
Thanks.
Yeah, no worries. This is my problem. I end up going, I'm too fast. Okay, so subspace prototypes. We're talking about directions. We're going to be talking about angles. That's where we're going. Why are these useful? These are just a couple examples to get you guys stoked. So in the left, we have these collections of images, and given a collection of images, you can make this thing called a subspace from a collection of images. So you have one subspace representing each one of these rows. And I'll be a little bit more formal about how to do this later, but essentially, there's one image that's in common in all three of these rows, and the illumination of the image is actually changed. It's actually my advisor, Dr. Michael Kirby. There he is there. And there's a really darkened version of him and even more darkened version of his face, right? And so we have three different subspaces. And if we calculate the flag mean, which is like the mean of subspaces in a sense with respect to a specific distance of these 3 points, these three subspaces, you get Dr. Michael Kirby's face. So he's the only image that's in common in these three subspaces, and this method for calculating averages using subspaces pulls out the common signal, which is kind of interesting, even though, you know, visually you can barely even see him in the second two subspaces. Okay. So the flag mean can pull out this common signal in subspaces, which is good, and it's sort of robust to changes in illumination, which is kind of the same as robust to changes in scaling. Okay, so now this second figure is kind of a two-dimensional embedding of k-dimensional subspaces that represent images of crops. You have different crop types. Blue corresponds to one crop type, green corresponds to another, and red corresponds to the third crop type. These are aerial images of crops. And it turns out that as you start with k equals 1, all these crops are essentially overlapping, these different crop types. There's no separation between them. But as you increase k, get to k equals 5, you begin to see separation between these subspaces. And when I say k, I mean these are now 5-dimensional subspaces of 220-dimensional space. So you're working in an ambient space, and you're working with a 5-dimensional subspace of that large ambient space. Again, for k equals 1, like for k equals 1 with a 220-dimensional space with k equals 1, these are just lines through the origin. For k equals 2, we're talking about planes that pass through the origin. For k equals 3, we talk about 3 spaces. Oh, that's kind of hard to visualize, but you get the idea. So once you hit 5, we see more separation. Once you hit 10-dimensional subspaces, you see almost perfect separation. And by the time you hit 15-dimensional subspaces, you're actually able to separate between these different crop types. So the idea is that these higher dimensional subspaces capture more variance in your data or in the individual classes of data points, and you're able to actually separate your data. So subspaces are useful, especially with computer vision data. Okay, so now we're going to formalize these subspace prototypes. Let's start with this object we're calling the Grassmann manifold. This is just, we're just thinking about it less from an, I guess, a strictly algebraic standpoint, and just thinking about it as a set. And this is really just a set of k-dimensional subspaces of n-dimensional space. So for example, GR12 would be the set of all lines through the origin in 2-dimensional space. So we need a way to represent points here, right? How do you represent a k-dimensional subspace of n-dimensional space? That seems kind of tricky, right? But what we're going to do is we're just going to use n by k matrices to represent these points. And these n by k matrices, the idea is that the column space or the span of the columns, so the set of all linear combinations of the columns of this matrix is represented by this, which is x in brackets, and that is indeed a k-dimensional subspace of n-dimensional space. If we require that, x transpose x is the identity. This is kind of like a weird linear algebraic restriction, but this is what we might call like an orthogonality constraint, because the columns in X are orthogonal to each other. In fact, we're orthonormal. So our goal here is to find a central subspace prototype Y, which is in which is an r-dimensional subspace of n-dimensional space of a set of subspaces. We have p of them, and each of them are different dimensional subspaces of n-dimensional space. So it seems kind of rough, but we will do it. So how are we going to do this? We're going to just write down optimization problems with orthogonality constraints to find the essential prototypes. And what about these optimization problems? They're going to either minimize distance between subspaces or maximize similarity between subspaces. And now, now we have an idea of how we're going to do this. All we need now is some sort of function that calculates the distance or similarity between two subspaces. Okay. So how are we going to do this? We're going to use this thing called the vector of principal angles. So we're using angles between subspaces to calculate distance and similarities. And let's just do a small example here. So if we take one-dimensional subspaces of two-dimensional space, these are just lines through the origin in R2. So here's X and here's Y. These are both unit vector representatives for the blue subspace X brackets and the Y subspace bracket of Y, the Y in brackets. And the principal angle between X and Y is just this one angle here, theta. But when you have higher dimensional subspaces, you have more principal angles between them. Yeah, cool. And notice it's the smallest angle between these two lines, right? You could also take this angle here, but that angle would be bigger. So we're taking the little one. So our principal angles have to be between 0 and pi over 2, right? If we're working in radians, which we like to do. So, given a vector principal angles between higher dimensional subspaces, you can formulate these ideas of distance and similarity between subspaces, right? If these two lines were closer together, the angle would be smaller, right? And also if the two lines were closer together, then the sine of the angle would be smaller, right? So those are sort of notions of distance between these two subspaces, whereas the cosine of the angle would be bigger if they were closer together. So that's more of a similarity. And specifically, since we're dealing with higher dimensional subspaces, we're calculating two norms of these vectors. So we have vectors and we have to figure out, well, we're going to do some sort of norm. And here we're going to calculate a two norm. If you don't remember what a two norm is, it's just our regular Euclidean distance, which is the square root of the sum of the squares of your vector. Okay. And there's a way to get at these angles given two arbitrary subspaces, and we can talk about that later if you're interested. So let's say we have a ton of different principal angles between subspaces. This is going to get a little hectic, but it's nice to see. I like to organize things and put them in tables. So why don't we, given a collection of points or a collection of subspaces and one central prototype subspace, can we generate some sort of matrix that contains all the information of the principal angles between this subspace Y and each of these xi's? And that's where we make this thing called the principal angle matrix. Hectic. But essentially each row corresponds to a point, or each column of this matrix corresponds to each of these xi's. And each row of the matrix corresponds to a principal angle number. And there are some details here. They're not as important. But essentially, now armed with this principal angle matrix, we can write down optimization problems and come up with subspace prototypes based on different norms of the principal angle matrix. And you can take a norm of a matrix by essentially like compressing the rows and then compressing the columns. Again, it's a detail that isn't as important as just understanding that there's a way to take a norm of a matrix, and depending upon the way you change the norm, you get a different prototype. As you saw with the Euclidean in Euclidean space, right? When we changed from not taking a square to taking a square, we got a lot of benefits. we got an easy problem to solve. But when we, so essentially, depending upon whether you take a square or you do different types of norms, you can change the convexity of the optimization problem and how easy it is to solve it. So here's one of the optimization problems. It was the solution is called the flag mean, and it was solved by my advisor, Dr. Michael Kirby, and Bruce Draper, and a number of other people. So there's another one, which is called the L2 median, which is kind of like the canonical median of subspaces in a sense. And this was solved by a couple of people that are interested in projects involving motion averaging and synchronization problems. It's pretty interesting stuff. It's commonly used in computer vision. And in the following section, if we get there, I can present my method for solving it for a specific case. Now I'm going to introduce this thing called the maximally correlated flag. It's been solved in specific cases by a number of different people, namely Moody Chu and Bates. And this is a maximization problem using cosines. And then the flag median is something that I introduced. We published a paper at CVPR, which is a computer vision journal and conference. And I can send you the link to the paper if you're interested in reading it. But essentially, this is kind of where it sits in terms of the theory. So we have some questions with these optimization problems, right? First off the bat, like whether or not we solve them, our question is like, well, are they convex at all? Like, is there always a unique flag median of the collection of subspaces? And yeah, also, what sort of properties do these prototypes have? So a quick example is if you take super evenly spaced subspaces, what would that look like? It would just be subspaces or lines. If we're talking about GR1n, these are just lines through the origin. And if we want them to be really evenly spaced, we just want all the angles between them all to be the same. And there's a way to like formalize this in a sense, using this whole field of really interesting, cool math called frame theory. But essentially, if you take a collection of vectors in Rn that form what's called an equiangular type frame, then you get vectors in Rn that are nicely spaced, which also means that the subspaces that they represent, or the lines that pass through the origin and those points, are also evenly spaced. So we're taking a bunch of evenly spaced subspaces. Now, what happens to our central prototypes when we do this? So the first thing that we noticed is that when you do the flag mean, which is this prototype that was developed by Draper, is that the flag mean of these super evenly spaced subspaces is in fact, the average of them is actually every point or every possible one-dimensional subspace of Rn, which is kind of funny. You're like, well, the mean should be unique, right? But this is like a total worst case scenario. It's just comical. I mean, perhaps in real data, maybe we wouldn't find something such perfectly configured data points, right? So we don't perhaps have to worry about this crazy fact, but it's interesting to note. The second proposition is that the L2 median and the flag median of a set of subspaces which span the points in an equiangular type frame. So it's just, if you take points that are really evenly spaced and you calculate either the L2 median and the flag median of them, then in fact, these two subspace prototypes are exactly each of the points in the data set. So you lose uniqueness, not quite as bad as the flag mean, but you get every other point in the data set. So the first proposition, we can say we've proven is true. The second proposition, however, we've only proven for even n, which is actually kind of funny as well. But it turns out that the odd n proof is still up for grabs. So yeah, if you're interested, we can chat about it. Great. Okay, so then there's another open question from this section, which is, can we determine where these optimization problems are convex for GRKN? So when we're dealing with k-dimensional subspaces, like how does that change our how does it change the convexity of these problems? Okay, so that's the first section. I think we'll probably just get through the computer vision stuff. Are there any what questions do you guys have about that first section? I realize there's a lot of theory, so. Okay. Michael, do we have until 12:50? Is that right? Or is it 12:40?
12:50 is good.
Sweet. Yeah, I'll just work through this. So we introduced these two new subspace prototypes, the maximally correlated flag and the flag median. And they're nice. They're interesting. Sometimes they behave well, sometimes they don't. That's all right. Now our question is, how do we actually compute these prototypes? Like I wrote down the optimization problems, but how can we solve these optimization problems? And that's where this flag IRLS algorithm comes in. Okay, so we have some inspiration that we need to begin with, and I threatened I would do this at the beginning of the talk. So given a set of points in Rn, we've got P of them. We're calling this set A. Now, how do we find just the geometric median of these points? This is an optimization problem that we talked about at the beginning. This is just a minimization of the Euclidean distance between your geometry. It's the minimizer of, I guess, the sum of the two norms. Anyhow, the optimization problem isn't too important, but if you write it down, you set the derivative equal to 0. When you solve it, you get this algorithm. This is the Weisfeld algorithm, which is discovered by Weisfeld. So let's initialize a guess for the geometric median. Then we repeat until convergence the following steps. Firstly, we calculate these weights, which look heinous. Again, this comes from taking the optimization, setting it equal to 0. You find these, calculate these weights. And then you do a, what essentially is a weighted centroid calculation. So the weights are Wi, and the centroid, right, is just add up all points divided by however many there are. And that is exactly what you do. And you just repeat these steps. You just continually calculate weighted means until you reach convergence. And in fact, this will be the geometric median of this set of points. So it's kind of cool. You're like calculating, at the initial step, you assign weights to each point based on your initial guess. And then at each step, you're changing the weights and calculating a centroid and updating them, because notice these weights are a function of your guess for the geometric median. And it turns out that eventually these weights will converge and you will get a point which represents the geometric median of your data. So one thing to note here, right, is, oh gosh, what happens if y is one of these xk or these xi? Well, then we're dividing by 0 and we can't do it, right? So there are these singularities in this algorithm that you have to avoid, or terminate the algorithm, or initialize at a new point if you're starting to divide by 0. Another thing that people will do is they'll add a small epsilon or a small number in the denominator of each of these fractions, and that will avoid, you'll never divide by 0 because you're always adding a little bit. Or you can take the maximum. There's two options here, but note you can divide by 0. This is an iteratively reweight the squares algorithm, which finds the geometric median of a set of points. Okay, here's the problem. Okay, so the flag mean is a least squares problem as well. It solves this optimization problem. I just kind of took the principal angle matrix thing that I showed you before that looked really hectic and kind of teased out this optimization problem. And this is a 2 norm squared problem. It looks very similar to a centroid problem, right? but you're dealing with principal angles or whatever. But regardless, you just see two norms squared. This is a centroid problem. And there's a solution that involves this decomposition of a matrix. And it's just a closed form solution. It's easy to solve, just like the centroid problem. So now the idea is what happens if we solve optimization problems with iteratively reweighted flag means. And that's literally all that flag IRLS is. So we take a set of orthonormal subspace representatives. We initialize a guess for the flag median or whatever optimization problem we're trying to solve. And then we repeat the following steps until convergence. We assign a weight and we calculate a weighted flag mean. And this algorithm can be used to find the flag median, the maximally correlated flag, and also the L2 median for one-dimensional subspaces. Okay. So let's say we have a data set now, and we're trying to use this algorithm to find the subspace prototype. SVD is the name of this singular is the name of this decomposition here. It's a nice thing, look it up if you have time, but essentially if you take, let's say, a set of videos and you vectorize each one of these videos, each frame of the video into a vector, and then you horizontally stack each frame, then you get a matrix, and then you do the SVD to get this sort of special matrix that satisfies this orthogonality constraint, and that gives you the subspace representative. So essentially, given a set of videos, you can make subspace representatives. Same thing with a set of images. Cool. So we did that, and this is, again, mildly hectic, but what we're going to do is provide some results from using these actual subspace prototypes on a computer vision data set, which is going to be a collection of images, a collection of video clips centered around a person performing an action. And specifically, this data set is the Mind's Eye data set, which is by Draper. And essentially, these are short black and white video clips centered around a person performing an action, and the action of the video clips is labeled. And so now what we're going to do is use these subspace prototypes within a larger thing called a clustering algorithm, which essentially just clusters similar points together using these prototypes at each iteration, and then see how they perform in comparison to one another. And when we do that, we see that this clustering algorithm, that the kind of the goodness of the clustering changes based on which representative you use. So the goodness of a clustering we're calling cluster purity, which is literally like how pure is the cluster based on the initial labelings. So how pure, like, for example, if cluster 1 all has label ride bike, then that would be a 1 cluster purity. And then, so that's on the y-axis, that's like the goodness of the clustering. On the x-axis, you have what's called the codebook size, which is just the number of clusters you're using. And essentially what we see is as you increase the number of clusters that you're using, you get a higher cluster purity. And in addition, for each of these clusterings, we see that the flag median has a higher cluster purity than these other two subspace prototypes. And this flag median was calculated using flag IRLS. This is kind of cool, right? Like if we compare my methods to previous methods, we see slightly improved cluster purities on the data set. So these aren't just like some wild harebrained idea for calculating central prototypes. These are actually like pretty darn useful, or at least outperform other known methods. Cool. So there's one open question from this section, which is, so we have a proof of convergence for flag IRLS for one of these subspace prototypes, but the question is there a proof of convergence for the other one, maximally correlated flag? What's the convergence rate? And these types of questions. So since we don't have time, biology stuff will be left. But this is interesting stuff, and these are other types of central prototypes that aren't necessarily subspace prototypes. And we'll go to the end here. This is good. I at least talk slower this time. So to conclude, we really only talked about 2 new subspace prototypes. We didn't get to talk about the other 2, but we have this flag median, and we have the maximally correlated flag. And then these cluster expression vectors, ING subspace, we can talk about later. We did talk about, however, optimization problems. We talked about iteratively reweighted least squares clustering algorithms. We did not get to our graph theory. It's okay. In our applications, we did talk about this computer vision application, but we didn't quite get to bioinformatics. Okay, thanks. What questions do you have?
If I may, I'll jump in and ask a question. Nate, I'm Dave Slutsky, and with the way Michael has arranged this, you guys don't know me, but I've been a longtime viewer of Michael, so I appreciate the opportunity to tell him thank you. I have a very glimmer of an idea of what you're doing, so not very in depth at all, but you just talked about how your methods are showing some improvement over some of the existing methods. When you have that improvement in purity, is that also coupled with a improvement in computational efficiency? Are your methods more complicated in computation? Do you get a benefit on both sides? Because as usual, we get one or the other, but not both.
Yeah, thanks, David. That's a great question. Yeah, so let's maybe go back to that big table. Yeah, and I regret, I guess I don't regret talking as much as I did. So essentially there are like these other methods, right? These other subspace prototypes. There's like this L2 median. There's this thing called the flag mean. And what we saw in that last example is that this prototype is best. So now the question is, well, is this flag IRLS algorithm that I introduced actually any faster than the state-of-the-art algorithm to compute the L2 median and the flag mean? So I would say the standard way to compute the L2 median from the experiments that I ran is slower. And I only have experimental evidence for this because I haven't been able to find the convergence rate of flag IRLS, which was that algorithm I'm using to compute this one. So I find that in examples, the flag median converges in very few iterations, and each iteration takes about the same amount of time as it takes to calculate one iteration for the L2 median. It's also an iterative algorithm. And then we also find that but we do find that the flag mean, in fact, is way faster to calculate than the flag median, because the algorithm that I devised pretty much does a flag mean at every step. So the algorithm like does this least squares problem at every step. So yeah, if it takes it k iterations to converge, then it's k times slower than the flag mean.
And as far as your comment about you talk too fast, I mean, you had a huge ambition to talk about all of this in 50 minutes. And Michael had this huge ambition, as we've seen as viewers of everything he's producing, where he's really trying to bring a whole slew of mathematics to the popular view. And I'm really thankful to both of you for doing this. And I had to squeeze it in between meetings, so I appreciate being able to get in here. And I apologize for a little bit of a late and rude entry. But one question that may be silly, but when you were talking about basically your coordinate system for identifying the elements of your Grassmannian manifold, you're using basically a orthonormal frame for each subspace. I didn't see anything that indicated you were removing the redundancy, because of course we can do any rigid motion on the subspace on that frame and get another coordinate for the same subspace. Maybe I'm being silly. Do you care?
No.
Or, when you do all of these optimization problems with all of these principal angle computations, et cetera, does it come out in the wash, or is that computationally expensive if one way or the other? So where are we worried about the redundancy in the representation for each of these elements of the Grossman?
Yeah, that's a good question. Yeah, so the question is like, if you take like one subspace representative, well, you can have multiple different representatives for the same subspace that aren't necessarily just since we're doing this unit vector thing, like, can you still have two completely different matrices that represent the same subspace? One way that you can think about this is just permuting the order of the columns of the matrix, right? And those would be two of the same. So for example, let's say you take a video, there's some intrinsic ordering in the frames of the video, right? And then you know, it would technically be the same video if you just change the ordering of the frame of the video.
Oh, so are you saying
Right?
in these applications, your coordinate for X is basically coming from the application, but when you do the optimization, you're doing it over general subspaces.
That's correct.
Okay, but so there's an issue in how you do that. Anyway, I have my next meeting starting in a few minutes, and
Okay.
part of it is I'm using 3 different systems, Zoom and Teams, all at the same time. But anyway, so I'm going to sign off. But thank you, Nate, again for this. It was very interesting. And Michael, again, thank you. I don't know if I'll have this opportunity again. I've been watching your videos now for a couple of years when a student found them for me. And man, you're insane. And
Oh, thanks.
And
are you David from University of North Georgia? Did I just find you?
You did just find me, yes.
Yeah. Do you want to do one of these?
No.
Okay, cool. Well, I thought I'd ask.
I appreciate that. I'm not really doing anything interesting these days. My focus is on freshmen and sophomores.
Okay.
And I'm mostly focused on the teaching side. I've dabbled enough so I can understand some of these words and try and frame a question that might be reasonable. But I'm not really doing any deep level stuff on my own. One of the things I'm doing later today is our math club, and I know you're involved in all these things as well.
Yeah.
And man, your videos and these other YouTube content providers have just been revolutionary in how we can engage conversations, engage students in conversations, right? And so
that's really good to hear from someone like
yeah.
outside of the scene, because sometimes like we just get locked into
no,
you know. So anyway, that's really good to hear. Thank you.
It's been fantastic, and I don't know how you keep up with everything you're doing, but your visions of everything that you're doing are just wonderful, amazing. I tell my students how jealous I am all the time that that they have this, and I didn't have that 30 years ago when I was their age. But it's just wonderful. So thank you for all you're doing. You're teaching me a hell of a lot of mathematics. But you're also inspiring just fantastic conversations with students. And so I have students who, you know, think of themselves as someday maybe going into engineering or perhaps even this kind of field, and to be even, you know, able to show them some of this stuff or talk to them about, yeah, here's a direction that you can take your training that may move you closer to this thing. But so anyway, I don't know if I'll ever have the opportunity to see you again, but I'm watching most of your videos. I don't know how a single human can watch all of them, much less make them. And I know you're prolific.
It's not healthy.
And that's a serious concern because you're doing amazing work. I hope you can do it in a sustainable way.
Yeah.
I'm a huge fan of what you're doing, and there's so many other wonderful content providers. It just is, it's a fun time to be around. And man, do you guys make it easy for me to talk to students and introduce them to neat stuff.
Thanks for all your kind words. It really kind of makes it all worth it, or helps make it all worth it.
Yeah. And I did get in here. I am giving you some money per month. It's under my wife's name because she's got the account. So
nice.
I was worried. I wasn't sure if I was going to be able to see this today, but I'm glad I was able to connect.
Yeah. Okay. Thanks.
And Nate, again, fantastically interesting stuff. Really wonderful. Maybe I'll have time to look into it a little bit more deeply. But thank you so much for doing this.
Yeah, no problem. Thank you so much. Yeah, awesome.
Yeah. And with
Good luck
that,
for the next meeting.
yeah, I'm going to that now. Thank you.
Yeah.
If I can figure out how to sign up. There it is.
Yeah, I have a question. So you
Yeah,
said that
what's up?
your method was at this moment computationally slower, although you hadn't proven some sort of like rate of convergence. Is some
Go
of
for it.
that perhaps because what you're testing it against is based on like algorithms that have been around for a long time and have been like optimized over and over and over again, and yours is just newly written perhaps, and so it could use some optimization? You know, this is me speaking kind of from an outsider of that world.
No. This is great. So flag IRLS algorithm. It's actually really interesting, just in terms of background. So there is an algorithm that is essentially the same thing ish. It is essentially the same thing that is called dual principal component pursuit, and that's been around for quite a while. And these are the algorithms that are really compared against when I did speed tests are the flag mean and the L2 median. And so the flag mean is really just one matrix composition, and that is it. You just matrix decomposition, you have the solution. You have the flag mean.
Okay.
And the L2 median, the algorithm to compute that I used to compare against mine, that algorithm is essentially it's kind of a Riemannian geometry game. And essentially what you do is, like, let's say you're trying to optimize some sort of function on a sphere, and you have like you have values for the points on the sphere, and what you do is like you kind of do like gradient descent but on the sphere, in a sense. And there's like kind of this gradient descent thing. I guess that's not Buxfeld, that's the Karcher mean, but the L2 median algorithm is like taking the Weisfeld algorithm that we talked about before, and adapting that in like the Riemannian manifold land, whatever that means.
Yeah.
And this is like kind of a lot, but essentially like that algorithm, you have to do at least one matrix decomposition every iteration and perhaps more. And that's what kind of that makes it, and in fact, it takes many iterations to converge, and there are like hyperparameters that you get to tune. So it's a bit more of a complex algorithm, and it generally does take longer to converge. And my algorithm, on the other hand, is to compute a different prototype, and it's just using the flag mean over and over, and in practice, it converged in very few iterations.
Okay.
But you can optimize. There is a person, I guess, in Germany his deal is like optimizing weights for these algorithms. They're just reweighted least squares. So that was something that I didn't do, but I should do, is reach out and see what his deal is, because he knows how to, I guess, do this sort of optimization of weights in order to speed up the algorithm even further.
So perhaps there are some gains to be made like that.
Yeah, totally.
Yeah, but I mean, from like a mathematics point of view, that's less interesting than coming up with it at first, right?
Yeah, I guess so. Yeah, I think that what I'm finding is really interesting right now is like the ties between this stuff, and from mathematics point of view, the ties between this stuff and frame theory, and like what happens to like what's an average of a bunch of really evenly spaced points, you know? And essentially, the two results that I said is like, well, if you try to take the average of a bunch of evenly spaced points, then average ends up being every point in the general space that you're working in, or it's each one of your evenly spaced points, which is like really weird. And so, I mean, maybe there are some questions there that could be answered.
When it feels like classically, it should be like just the center of mass.
Exactly.
Yeah, but I mean, you're measuring something different, obviously, right? And a lot of so another thing that I have a question about, which is really like kind of a broader question, is that a lot of the terminology seems to come from like modern geometry ideas. Although most of the stuff that you wrote down was like pure linear algebra, right? So the idea of like a flag and a flag manifold and like all that kind of stuff, so that comes from like geometric ideas, and your Grassmannians come from like Riemannian manifolds and Riemannian geometry. But like at the same time, it was just like linear algebra. So what is there like a translation? Like why are those terms being used? Is that linear algebra really like some sort of deep connection to maybe metrics on those manifolds or something? I don't know. It's not a very well formed question, but I think maybe the point.
Totally. It's like, dude, you're doing, I mean, it's not that like, what I'm doing isn't that complex when it comes down to it, right? Like I'm just doing linear algebra.
Yeah, I mean, and I didn't mean to like downplay it like just linear algebra. Obviously, linear algebra is like with the most powerful subject that like we've come up with.
Yeah, for sure. And it's great. So essentially, like to be on these spaces, right? When I talked about representatives, this is going to take forever to get back, but we had this like orthogonality constraint.
Right.
And that kind of, as long as you're dealing with matrices that satisfy this orthogonality constraint, you're living in the space.
This is now kind of like a projective space, right?
GR1n is n plus one dimensional space.
Got it. So it does have some relation to some projective space.
Yep. And then so I mean, so that's the first thing, is like the way that we're representing points on this manifold is in this manner. And this gives, like, if you think about the manifold can be written down as like a quotient of, and this is what I should know well. You can write it down as a quotient of two orthogonal groups, or orthogonal groups, depending on what you're dealing with. And
it's some sort of oral exam question.
This gives you like an equivalence class. Yeah. It gives you an equivalence class. And then when you talk about like distances between these points, the canonical like Riemannian metric, I believe, is this geodesic distance, exactly written like this.
Yeah, sure.
Which, and in fact, can be written in terms of log and x maps.
Like up to the manifold and down to the tangent space.
Yep.
Like Lie groups and Lie algebras.
Yep.
Cool.
Yep. Yeah. So there's this tie to like Lie theory, but when you get down and compute all these things, like to compute this term here or this term here and this term, you can get at the cosine of the principal angles by just doing the trace of matrix products, without having to do any matrix decomposition or any like heavy machinery.
Yeah.
So that's nice.
That's interesting. Any other questions out there in Zoom land? All right. Well, I don't know, maybe we'll call it then.
So it's a good place to stop, as they say.
Thanks, dude.